Before we continue, one student had a question about question 5 on homework 6.5. So let's go over that first. So let's see what question 5 was. This is question 5. Seems kind of long. All right, so actually, you know what? It's probably better for me to share the browser. Okay, so here's question 5. The graph shows data traffic on the link from the United States. I don't think any of this matters. Here's a graph. So they want you to use which rule is this? Simpson's rule with 12 subintervals. And they already gave you that delta t is 3600. And they want you to use Simpson's rule. Okay, well, it seems like they gave you all the numbers already. You just need to plug all this into a calculator and get the answer. What was the issue exactly with this question? Oh, you just misread it? Okay. So are you good then? Yeah, okay. All right. In that case, if anyone else doesn't have any further questions, we'll continue 6.6. And yeah, we'll definitely finish early today because we only have like a few more slides. How far did we get yesterday? Let me see. We did this. Okay, so this was the last slide we did last time. Examples of type 2 integrals. So now we're going to go over this thing called the comparison test for improper integrals. So let's just read the slide. Sometimes when we evaluate improper integrals, we might not care about what value it converges to. So for example, for previous examples, we got a value for the integral, so we say it converges to 0 or something like that. But sometimes we'll just say it converges. Also, there may be times where we are faced with unintegratable integrals, but we still might desire to know whether they converge or diverge. Yeah, so a technique to do this is called the comparison test for improper integrals. So how does this comparison test work? So here it is, the comparison test. If you have two functions or two positive functions, they all have to be greater than or equal to 0. So your two functions are f and g. And this part is very important. F is the bigger function and g is a smaller function. So the test says if f converges, then g converges. So what it's saying is that if you have the bigger function converge, then the smaller function also converges. Okay, and then the second part says if g diverges, then f also diverges. So that one says if the smaller function diverges, then the bigger function also diverges. Okay, so that might have sounded a little bit confusing, but to sum it up, it's basically saying that integrals less than convergent integrals are also convergent, and integrals greater than divergent integrals are also divergent. I wouldn't recommend you guys memorizing this. It's a lot easier if you just use your intuition. So remember that divergent means the integral already goes to infinity. So if you have an integral that's divergent, so it's already some sort of infinity, then anything greater than that integral is also going to be infinity and therefore divergent, okay? And same with convergence. So if you have a function that's convergent, so it's already a finite value, then any smaller integral will also have a finite value, which is also convergent, okay? So hopefully that makes intuitive sense and you don't need to memorize this. So the question is, well, we need to have one function that we already know whether or not it converges or diverges. So what function do we choose? And the majority of the time, this known integral will be in the form that we discussed earlier, which is the 1 over x to some power. Yeah, from last time, we looked at two integrals, like 1 over x and 1 over x squared. So that's usually one of the functions that, or one of the integrals that you're going to compare it to. All right. You guys are muted, right? Did I mute you guys? No. You guys are just not talking. Okay, so so the way you set up the comparison test is you set up two integrals and then you have an inequality. So once you have your inequality, you try to reach a conclusion for the comparison test. So let's look at some examples. Here we have 3 examples. And we'll do these right now. So let's look at the first one. So first thing I'm going to do is just factor out the 38 because that really doesn't change anything. X over x to the third plus 1. Now, I'm going to write another integral, and then what I want you guys to tell me is what inequality sign should I put between the two integrals? So we have this one, which is the one we have right now. Compare it to this one right here. So
you forgot to switch.
Yeah, thanks.
No problem.
There. So so we have the original integral, which I factor out of 38, so we're left with x over x to the third plus 1. And then I'm going to write this one right here, x over x to the third, which I'm going to compare it to. So can you guys tell me what inequality sign should go between these two integrals? Would it be a greater than or less than?
Less.
One person says greater than, another person says greater than, less than. Why did you choose x over x to the third? We'll get to that in a little bit. But for now, just try to figure out what inequality sign should go there. Someone said less. Why do you say less?
Well, let's say if we plug in x equals 1, right? So it's on the bottom be 1 plus 1, 1/2, and then 1 over 1 is 1. So it's going to be 1/2 is less than 1.
Yes. Yeah, that's a good way of deciding. Just choose a number for x. Another way you could have reached that conclusion is just to say, well, the only thing different between the two fractions is this one right here has a bigger denominator because there's a plus 1 in the denominator. And bigger denominators mean smaller fractions. So that's how I would have reached the conclusion, but whatever works. So it's a less than. Okay. So what I'm going to do is I'm going to write the integral back in. So this integral, x to the third plus 1, is less than this integral. That's what we just analyzed. But this integral that I chose is, you can reduce that, right? So that's 0 to infinity of 1 over x squared. And this integral 1 over x squared, do you guys remember what we said about that integral from last time?
It's convergent.
Yes, it's convergent. So remember that when it's in the form 1 over x to some power, if the power is greater than 1, it's convergent. So this is convergent. And then our original integral, which is this one right here, this is less than our convergent integral that we chose to compare it to. So what do you guys think we can conclude about our original integral?
It's also convergent.
Yes, there you go. So this is also convergent because it's less than another convergent integral. So that's really how the comparison test works. Yosef, to answer your question, why we chose x over x to the third, it's because that's 1 over x squared, and we know whether 1 over x squared converges or diverges. That's why we chose that one. Okay, so that's the first example. The answer is convergent. Are you guys okay so far? Okay. Let's look at the next example. Okay, so this one is cosine squared of x over x squared. What do you guys think would be a good value, or sorry, a good integral to compare it to? Any ideas?
Make the denominator x squared plus 1 again.
Make the denominator x squared plus 1. I mean, you could, but keep in mind that we want to compare it to another integral that we already know whether or not it converges or diverges. So most of the time, it's going to be in the form 1 over x to some power. So that should give you a hint as to what the best option is.
Can we just do 1 over x squared, or
Let's see. Let's think about that. 1 over x squared. Well, if you do choose that one, what will be your inequality sign?
that's a good question. I don't think you could put 1.
Well, I think this might work. So cosine squared, right? If you think about what's the range of a cosine graph, I think it goes like this, right? So it goes between -1 and 1. Yeah, that's right?
Yeah.
So if you were to say compare the two numerators, so this numerator and this numerator, do you guys see how whatever value you get for the range of cosine is always going to be less than 1, right? Because the range of cosine goes from -1 to 1, like it oscillates between -1 to 1. So it's always going to be less than this numerator. Are you guys okay with that?
But can it also be exactly equal to 1 as well?
Yeah, but I think, yeah, but if you put less than or equal to, that should still be fine. So are you guys convinced that this is okay?
Semi.
Yeah, I mean, it should be fine because the denominator is the same. So the only thing we're comparing are the numerators. And the value of cosine squared is not going to exceed 1 ever. So this should be fine. But 1 over x squared, we already know the answer for that one. 1 over x squared is convergent, right? This is convergent. So if our original integral is less than a convergent integral, what do we conclude?
It's also convergent.
Yeah. So this one is also convergent. Okay, so that's example number 2. Let's do one last one. All right. Here we have integral from 1 to infinity of 2 times x plus 1 over square root of x to the 4th minus x. First thing I'll do is just factor out the 2. So I'll put on the outside because that doesn't really affect the convergence or divergence. So we can just look at everything besides the 2. And then let me show you guys what would be the best option for this one, since this one is not so obvious. First thing I'll do is I'll get rid of the 1 in the numerator. So consider this integral here. X to the 4th minus x from 1 to infinity. Now, if you were to put an inequality sign between these two integrals, so this one and this one, what will be your inequality sign? Greater than? Yeah, why greater than? Yeah, so the first integral has the bigger numerator, which is why it's greater than. So this would be greater than. Good, okay. Yeah, the issue here is that our second integral, we still don't know much about it because it's still not in the form where we know like whether it converges or diverges. So we have to keep going. Consider this one right here. So I'll have the numerator stay the same, but in the denominator, I'm going to take out the minus x. So consider this one. What do you guys think would be the inequality between the second and third integral? Less than? Let's, I don't know, it's not so obvious. Everyone agree with less than? Will the second be greater than? Yeah, so people who gave an answer, like maybe justify why you think it's less than or greater than. Yosef, do you have a reason why you say less than? Okay, then greater than because the lower denominator means higher number. So I took away the minus x, which is the only thing missing. Less than. Subtracting 4 would make the denominator smaller and overall expression would be greater. Yeah. So what would the inequality be? Yeah, so I think that's a pretty convincing argument as to why it's greater than. The easiest way to see would just be to plug in a number, just to convince yourself. So if you plug in, say, like 4, so this will be 4 over square root of 16 minus 4, and then you compare that to 4 over square root of 16. So this would be 4 over square root of 12, and this would be 4 over square root of 16. The first one has the smaller denominator, which makes the overall fraction greater. So yeah, this is greater than. Now, some of you guys might be wondering, well, it's an x. What if we plug in a negative number for x? Wouldn't that change the inequality? The answer is no, because you're not allowed to plug in a negative number for x because our limits of integration don't include negative numbers. So this strictly is a greater than sign inequality. All right, now that we established that, let's keep going. I can simplify the third integral, right? So this is equal to integral of 1 to infinity of x over, the square root of x to the fourth is x squared, which is also equal to 1 over x, right? Okay, so 1 over x, this should be an integral that we recognize. And do you remember what we said about this integral, whether it's convergent or divergent?
It's divergent.
Yes, this is divergent. So let me mark that down. If this integral is divergent, can we conclude anything about our original integral?
The original is also divergent.
Yeah, and the reason is because can you finish the reasoning?
Because if the original function diverges, then if the comparison function diverges, then the original function does so as well.
Well, not always, but you're missing one key part of your answer. So the part you're missing is that our original function is also greater than the comparison function. So let me just restate that. So our original function diverges because it's also greater than another divergent function. Yeah, just like that. Okay, so this is how the comparison test works for 3 examples. Any questions so far? How do you pick a value to compare? Well, we didn't pick a value. You mean like how do you pick a another? Like how do you pick another integral? Is that what you mean? One over x. Yeah, I mean the process is basically you look at your original function and you try to strip off the terms until you get it in the form 1 over x to some power. So like you look at this function, like it would be really good if the +1 wasn't there and the minus x wasn't there, because then you could simplify it to 1 over x to some power. So I just strip away the 1 and I strip away the negative x, and then I see where the inequality goes. And then it just so happened to simplify to this. All right, so before I give you guys some more practice problems, I just want to make a note about cases where the comparison test fails. So let me go back to the PowerPoint. So here we have the comparison test. So it says, no, in some cases, the comparison test will be inconclusive. Now, going back to how to reach a conclusion, can you guys think of the situation where a comparison test fails? Actually, let me go back to the question we just did. So let me go back to this one right here. So let's say for this example, we didn't reach a conclusion yet, but here's our inequality. And let's say we got some integral here and we analyze it. And let's say this integral here was not convergent, but this was divergent. So we have a divergent function, and then our original integral is less than a divergent integral. What do you think would be the conclusion here? So keeping in mind that divergent means this integral already goes to some sort of infinity, and our original one is less than that.
Wouldn't we say it's still divergent since it's less?
Maybe. Can't it also be like a finite number because it's less?
Maybe we could use the p-value to determine if it converges or diverges.
What's the p-value?
Well, in the original, it's x to the power of 3, so maybe we could use that 3, and 3 is greater than 1, so we know that it converges.
I think you're using like another technique, but I don't think that that's how the comparison test, like I don't think that's a process for the comparison test though. What I'm trying to get at is like, if you have a divergent integral, which is this one here, and then you have an integral that's less than a divergent integral, then your original one can either be divergent or convergent. That's the issue. Because if I tell you you're less than infinity, you can still be infinity or you can be a finite number. So this is really the case where a comparison test would fail. So in this case, you would say it's inconclusive, because being less than infinity doesn't guarantee you to be infinity or not infinity. So that would be when the comparison test fails. And the same thing for this one. So if we got convergent here, and we had a integral that's greater than a convergent integral, then that's also inconclusive, because greater than a finite number can still mean finite or it can mean infinite. So I guess be careful with the inequalities, because sometimes you can misuse the integral. Sorry, you can misuse the comparison test, and you can reach the conclusion that it's inconclusive. Anyways, I'm gonna put some more examples up for you guys to practice. So I want you guys to try these. Remember that you always want to compare the original integral to an integral that we already know. So usually 1 over x to some power p. All right, I'll give you guys 7 minutes. Yeah, these examples here. How are you guys doing? Are you guys doing okay? All right. No one responded. So I'll assume that you're all okay. And then anyone else need extra time? All right, let's go over that. Okay, so for the first one, what's the next integral to compare it to?
One over x squared.
Yes. So the numerator is the same, but the denominator, we got rid of the plus 2x. So what's the inequality sign here?
Less than.
Less than, yes. And the reason it's less than is because the original integral has a bigger denominator, so it's less than. Okay, so that's fine. 1 over x squared, we do know what that does. So what does 1 over x squared do?
Converge.
Yes, very good, converge. And then our original integral is less than a convergent integral. Can we reach a conclusion here?
Yes, we can. That it converges.
Yes. So our original integral also converges because it's less than a convergent integral, right? So convergent means this one already has a finite value, which means this one also has to have a finite value because it's less. Okay, good. All right. Number 2. So does anyone have a good integral to compare this one to? Fact out 32. Okay, I'll do that. So this is 32. We can just ignore the 32 because that doesn't change the convergence or divergence. All right, now what?
You could compare it to 2 over x.
Yes, 2 over x. What would be your inequality?
Greater than?
Greater than, is that right? Why greater than?
Because the denominators are the same, but the numerator for 2 plus e to the power of negative x is slightly greater.
Yeah. So this term basically adds value to the numerator. So when you take that away, it makes the numerator smaller. So our inequality is greater than. 2 over x, you can basically write that as 2 times the integral of 1 over x, right? So what do we know about this integral here? We recognize that.
It diverges?
Yeah, right, 1 over x diverges. So this is divergent. Can we reach a conclusion of our original integral or no?
We can, because the original is greater than the comparison.
Yeah, so our conclusion is that this also diverges, right? Okay, great. What do you guys think about this so far? Do you guys find this like easier than the stuff we've done or harder?
I disliked this stuff so much when I took BC.
Really? What was the thing that put you off?
I don't know, I studied it on my own and it didn't make sense on my own. Now it does.
Oh, well, that's maybe it's because you need to look at it a second time. It's not too bad. It's 50-50. What does 50-50 mean? I have no idea.
Like these specific questions aren't too bad, but it could get worse.
Yeah, I guess. All right, let's look at the last one. So here we have integral of 1 to infinity of 1 over x squared minus 6. Okay. Who thinks they have a good integrals to compare it to?
1 over x squared.
Okay, so you took out the minus 6. What's your inequality sign?
Greater.
Yeah, because the first one has a smaller denominator, so it's greater. Yeah. Okay, 1 over x squared. We know that one. What does that one do again?
Converge.
Right, so this converges. So can we reach a conclusion for our original integral?
No.
No. What? Why not?
Because the original is greater than the comparison. But it
Okay,
should be
but then what's
less.
the issue? Why can't we say the original one converges as well?
Because the comparison should be greater than the original.
Comparison be greater than the original. Yeah, I mean, that's a weird way of wording it, but yeah, I guess you're right. So yeah, it's greater than a finite number. So being greater than a finite number doesn't guarantee you to be finite or infinite. Yeah, if this was divergent, then we could say the original is divergent, but we cannot. So for this one, you would have to say that this is inconclusive, and the comparison test failed. Okay. Okay, any questions? All right, well, just a comment on how these questions can be made harder. So in all the examples we've comparing it to an integral in the form 1 over x to the p, some power p, which sort of makes these questions quite simple. I know what some teachers do is they make you compare it to a previous problem. So instead of comparing to 1 over x to the p, like they might make you compare number 3 to like number 2 or something, because you have an answer for number 2, so then they make you compare to that, which I personally think is too much to ask for. So I'm probably not going to do that. But I guess this is pretty much how it goes. So this is comparison test. And make sure you know how to use it, and make sure you know like when it's inconclusive and all that stuff. Other than that, you should be fine. So guess what? This is all we have planned for today. So we're done with 6.6. I do have some announcements before I let you guys go. So just stick with me for 1 second. Going back to the PowerPoint. Okay, so on your free time, you guys can do homework 6.6 because we've finished this section. And then 6.6 is also the last subsection of chapter 6. So on your free time, also try doing the chapter 6 quiz. You guys probably noticed this, but I moved all the stuff on Lumen into one section just so it wasn't like confusing everyone. I finally figured out how to do that. And then last thing I want to look at is the syllabus. So let me pull that up. Is a test November 12th. Honestly, I still don't know yet. I'll have to look at the number of topics remaining. So here's the syllabus. We are on, well, we just finished 6.6. So if you look at the list of topics, we have 7.5 or 7.4, 7.5, 7.6, 8.1, 8.2, and 8.3. So 6 more topics. All right, here's what I'm gonna do, guys. So 7.4 through 7.6, we're gonna skip all of it. And here's the reason why. So 7.4 and 7.5, those are not the essential topics of Calc 2. So what we're gonna do is for 7.4 and 7.5, we'll only go through those if like at the end of the semester, we finish early and then we have literally nothing else to do. So we're gonna skip 7.4, 7.5. 7.6, that one is best to do if I have like physics students in my classroom. I looked at the roster of this class and none of you guys are physics major. So we're gonna skip 7.6. Which means the next time we meet, we're actually going to start chapter 8. And that's sequences. So yeah, it's like mostly computer science majors. So we're gonna skip the physics stuff because I don't think any of you guys care. I don't care, you guys don't care, so what's the point? Sequences also marks like the midpoint of Calculus 2. So we're pretty much 50% done with the curriculum. Yeah, so all the methods of integration from like the first thing we did all the way up to improper integrals. We're done with methods of integrating. So next time we meet, we're going to talk about all new stuff, which is what are sequences and series, which is, you know, all things that I think computer science majors care about because that's what you do. So yeah, that's just a look into the future. Let me see if I can estimate when I should put the next exam. So we have 3 more topics. We have sequences, series, and the integral and comparison test. I'm going to estimate 4 more lectures. So each one should take 1 lecture, but probably one of them will take more than 1. So if we take 4 more lectures, then that means we have October 26th, no wait, that's Monday, October 27th, 29th, and then November 3rd, November 5th, and then review for November 10th. Okay, yeah, November 12th does seem reasonable. It is possible that the exam's on November 12th. So yeah, that's just an estimate. So nothing is confirmed yet, guys. I still don't know when the test will be, but the estimate is November 12th. I'll update you guys once once I'm like sure of it. So yeah. Any questions? Sounds good, sounds good. All right, everyone say sounds good. Okay, well, if everything sounds good, then let's stop here. And I'll see you guys on Tuesday. Have a good weekend.